Hey everybody, it's Mr. Carr again. Today we're going to be looking at 2.2 day 2. Today's focus is going to be the applications of quadratic functions. A lot of this has to do with something like this. Objects that fly through the air. Real life, because of gravity, something goes up in the air and then it comes down again. And it follows a parabola shape to that path through the air. So that's what our focus is, and we're going to use that to model some real life scenarios. Like, for example, a football is thrown through the air and follows a parabolic path. Following function gives the height of the ball, h, in feet, t seconds after it's thrown. So we're looking at this one right here. So establish an appropriate viewing window on your graphing calculator. So I'm going to go ahead and just pull this up into Desmos so you can see that one, but TI-84 is going to work as well. So give me a second on that one. Okay, so here I am in Desmos. This is our basic version of this one right here. It's like pretty much our main window. You're going to want to change that window up so you can see more of this. One of the things we need with these word problems, sometimes we like to look at, hey, how high does it go? What's our maximum height? So I want to scroll this up here. I want to zoom out a little bit until I can see my window all the way up to there. Okay, if you're doing this in a TI-84, you're going to want to hit the window button and kind of play around with it. So you're changing the Y mins and Y maxes. Notice here I went all the way up to at least 100 in the Y direction. The X direction, I don't have to go that far. And if I want to do something a little bit more with that, I can actually do this. Instead of me having such a very skinny parabola, I can kind of expand out the X and just focus in on this small section. So I'm going to leave Y alone, but I'm going to change X to, let's just go like a little -2. And then over here, we'll make it, we know, I don't know, 10 is enough right there. This gives us a better view for what the path is following. So here's the path of the football. It goes up in the air, and then it comes back down, and then boom, it lands on the ground right there. Okay, so Desmos is very handy for that, for finding a lot of these things. So first thing I'm going to do is let's look at this. At 2.5, it's up to a 104. That's a maximum. Down here at 5.04951, it's at 0. What do those points mean? So let's come back here and analyze that. So once we had that view, we saw, oh, well, we got a different one. Let me jump it around a little bit. Let's talk about the maximum height of the ball. At what time does it reach its maximum height? That's that vertex. So remember that vertex looked like this. It was 2.5, 104. Okay. So when I say the maximum height, I just put my vertex into the context of the problem. Height was feet. T is seconds. So if I look at this one, if I answer this two questions here, I would say at 2.5 seconds, 2.5 seconds, the maximum height is 104 feet. That's my vertex right there. I'm just interpreting into the problem. That's all. Use my graph to find the height of the ball after 1.5 seconds. So a couple things you can do with that. You can actually do something similar in your, oops, I zoomed in a little too much there. There we go. All right. One thing you can do here, if I want to find it at 1.5 seconds, that is in the X direction. So let me graph this. X equals 1.5. Notice that it intersects there. So I can click on that spot and I see at 1.5, it's at 88. Okay. So that is like one quick way to do it there. If you wanted to, you can just click that and drag it until you got to that 1.5 mark. Sometimes it's a little bit tricky when you do it that way. The other thing you can do is you can click in Desmos, you can click, let's see here. Yeah, you can click up this gear wheel. That first little option right there, this one makes it look like a table now. So if I click that where it looks like a little mini table, I click that and now I have a table. So one thing I can do with that is I can just type in any number I want, like 1.5. And there it is at 88. Multiple ways we can use our graph with Desmos here to help us find that. Bottom line is we know that the height of the ball, height of the ball is going to be 88 feet after 1.5 seconds. Okay. So let's move on to another one. A go-kart track has about 380 racers per week and charges each racer $35 to race. The owner estimates that there will be 20 more racers per week for every $1 reduction in the price per racer. How can the owner of the go-kart track maximize the weekly revenue? Here's what we want to look at. Revenue is made up of price times the attendance. Okay. So in order to do this, we're going to set up, like we start with our like kind of established facts. 300 racers will show up if it's $35 to race. So the idea is that the revenue, I'll just call it R, is going to equal to the price 35 times the attendance, which is 380. Now I left this open because look at what happens. The owner, if we do a dollar reduction in the price, so I'm representing that as like one minus 1x, we expect 20 more racers to show up. So that means that I'm going to do 20 plus 20x here. This represents, like in this scenario, I should write this down as well, but x is actually representing the number of price reductions. Okay. So instead of it being an exact value of x, like what it is, I'm actually saying like this is how many times we're going to reduce the price. Okay. Every time I reduce the price by $1, this goes up by 20. What I have is I have a quadratic. Doesn't quite look like it yet, but I do. So one thing I can do is technically I could go graph this right away and find my maximum revenue if I wanted to. I'm going to go a little bit more algebraic on this one. First thing I'm going to do is I'm going to distribute here, turn it into standard form. So my revenue is going to equal to, we got 35 times 380. Comes out to 13,300. And then we have 35 times 20x. Going to get me 700x, then -1 times the 380. So that's negative 380x, and then -1x times a positive 20x, which is a negative 20x squared. Combine my like terms here. So R is going to equal to, now I'm going to rearrange it, negative 20x squared. Put these two together. So 700 minus 380 gives me a positive 320x plus 13,300. Okay, so we want a maximum revenue. So I could go and graph this, or I can do my x equals negative b over 2a. We can do this with our just algebraic methods if we wanted to. So I do negative b, that'll be negative of 320 over 2 times a negative 20. So that's going to be a negative 320 divided by a negative 40. When I do that, I reduce it, that's x equals 8. 8, remember, this is the number of times we reduce the price. So 8 represents taking our $35 and we subtract 8 away from that. That's going to be our new price that gives us our maximum revenue. So how can the owner of the go-kart track maximize weekly revenue? So yeah, if I answer this completely, we're going to say that we can reduce the price by taking 35 minus 8 to give me $27. Okay, so the go-kart should charge $27 is the idea. Okay, now it didn't quite say it here, but we can also find that maximum revenue price by plugging it in here. So by plugging in the 8, x equals 8, I can do it either here or in here, doesn't really matter. So if I represent my revenue as 35 minus 8 is 27, multiplied by 380 plus 20 times 8. Okay, so my revenue will be 27. Oops, let me write that a little better. 27 times, we got 380 plus 20 times 8 is going to give me 540, which is then going to come out to $14,580. Okay, so the idea here is that to maximize weekly revenue, the go-kart place should charge $27 for racing, and that'll lead to a maximum revenue of 14,580. Okay. I believe one more here. Yep. Last word problem to go over, our last application. An electronics store sells about 70 smartphones per month at a price of $320 each. For each $20 decrease in price, about 5 more smartphones will be per month are sold. Write a function that models the situation. Okay. So our function, again, we're trying to maximize revenue here. So if I do that, that's going to be R is equal to, I start with my selling price. Well, I should actually start with defining my variable. So I'm going to say X in this scenario is going to be the number of price reductions. Okay, so we start with our selling price. We can start with, that's what I did there. So R for revenue is going to start with our price, which is 320, minus for every $20 decrease. So I'm going to take minus 20X. And then we get 5 more smartphones. So that means that my number of 70 is going to be added by 5X. Okay. Now, just to show a little bit more with our Desmos and other graphing utilities, I'm not going to do this one by hand. I'm going to go back to Desmos and take a look at that. One nice thing about Desmos is I can just type it in exactly like this. And it's a little bit, well, you could do that in TI-84s as well, but I think it's a little bit easier in Desmos. So that's 320 minus 20X and then 70 plus 5X here. Okay. Does it again. Get rid of that old one. So we got parentheses 320 minus 20X parentheses, and then another one is going to be 70 plus 5X here. Okay, change your window around. You're dealing with some pretty large numbers here, so I'm going to go way up top. The only thing I care about here is what is the vertex. Okay, so I'm using technology to make this a little faster for myself. All right, now I can see that. I zoom in a bit here. 1. Okay, so at 1, now it's important to understand that 1 as 22,500. So I come back here, my vertex is at 1, 22,500. Okay, so how much does the store charge to maximize the revenue? Remember, X is the number of price reductions. So that means we start at 320, they should charge 320 minus 20 times 1, which gives me, well, 320 minus 20, so $300. So they should charge, I didn't finish writing the word charge, they should charge $300 to maximize the revenue. What is the maximum revenue? Well, that's the Y value here. We get a maximum revenue of $22,500. Okay, so again, that's it for today. We're looking at those application type of problems. How do we model some real life scenarios with our quadratics? 2 very common things would be projectile motion, like things flying through the air. They follow a parabola shape with their movement. Or we do stuff like this, where we want to maximize revenue, or some other types of things we want to minimize costs, things like that. Okay, so that's just something that we're looking at for things like this. All right, so again, you're looking for those key things. Vertex has a lot of real life meaning to it, so it's a good thing to help analyze as part of our problems. So just make sure you understand how to find it either graphically with your technology like this, or doing it algebraically. So in this problem, I could have distributed out, turned it into standard form, could have found the exact same vertex that way. All right, that's it for today. Take care, everyone.